The definition for least squares was defined last time, and we defined this thing called the normal equations, um, and we got this from the relationship between the ax and the b that we're trying to define, the project, and all that. And so we have a set of normal equations would be if you have a system ax is equal to b that you're trying to solve for, and you don't have solutions for x. We can try to get as close as possible using some of those projections, and we can define what's called the normal equations by looking at the transpose of A and then multiplying that by B on one side of the equation, and a transpose multiplied with the original A, and then we're solving for X. Solving for X, and since we don't have solutions for AX plus B, then I think the book decides to call it X hat, to say that's that's the closest we can get, even though we're not going to get the exact solution for this. X hat will be our solutions to the least squares problem. So the least squares problem breaks down to something like solving for this, and then the theorem that follows that says that if you have an n by n matrix, then we have logical equivalences that's similar to, the A through O, P, Q, or whatever, however far we went with the inverse matrix theorem. So this is referring to the idea of being able to find the inverse of something. Now, we can only find inverse of square matrices, right? And so A does not necessarily have to be a square matrix, but it turns out that A transpose times A will necessarily have to be a square matrix. So the equation AX plus B has a unique least square solution for each B in some vector space, and the columns of A are linearly independent. And as long as that's true, then the AT, the transpose of A times A, is going to be invertible. And in those cases, if we could just find the inverse of that, I don't know how easy it would be, but if we can find the inverse of those matrices, then then we can solve for these problems really quite easily. Well, not quite, because remember that the matrices have to be square, and A is not necessarily a square matrix, and so we can't. It'd be nice to take advantage of that theorem, but we can't necessarily do it for this. And I think we did an example. We did this example already. Let's see if we can find another example. So let's do this example. We have A is a 4 by 3 matrix, and then we have B is a matrix living in R4. So the solutions, by the way, for us would be in R3 somewhere, right? That's the number of columns. So that's the our solution X or X hat should be coming from that vector space. We have to find the inverse of a 3 by 3 matrix, it looks like. It's okay, we have that. Hopefully, we'll see. All right, so let's take a look at, well, it looks like our solution is just going to be this, so why don't we just find that? Should we do it by hand? Well, let's think about this. Just for the sake of fairness, does everybody know how to use their matrix stuff in their calculators? Does everybody have at least a TI-83? Okay. All right. Then then learn. So yeah, it would be a 4. Oh, so we have to find the inverse of a 4 by 4. It's a transpose first, so it's a 3 by 4 and 4 by 3, so it'll be a 3 by 3. So okay, I'm gonna go ahead and find it using MATLAB. Who's gonna supervise? All right. So we have A transpose and A, and then we can figure out what. Maybe I should pop this window out. Can I pop this window out? So I want A transpose times A. Wow, look at that. Okay. Oh, we'll see. So it turns out that A times, or A transpose times A is 3. So if we figure out what the inverse of this is, what is the inverse of this? I don't know. I need to multiply this by something so that I get 1 identity. So that's the inverse. And then I'll multiply that by A transpose. Actually, it might be better if you do A transpose times B first. So A transpose times B is going to be the transpose of this, which is going to be 1, 1, 0, negative 1, 1, 0, 1, 1, and 0, negative 1, 1, negative 1. And B is 2, 5, 6, 6. So when we do this multiplication, this is a 3 by 4 and a 4 by 1. What should we get? A 3 by 1. So this is that's 7 minus 6. 12, 14, and negative 5. And so we need to figure out what x. So our solution to our least squares problem is going to be x time is equal to the A transpose A inverse times ATB, and that's just going to be 1/3, 1/3, 1/3 times 114 negative 5. So what is it? 1/3. So this is our solution, and we're done. So these are the x values. Remember that these are the x values that go in and produces the solution. Yeah. Yeah, four dimensions. We could. So yeah. So what we want to do to figure that out is remember that ax bar, this is our solution, x hat, ax hat should be close to b, as close to b as possible, right? So, yeah. So what was A again? A is that, and then x bar 1/3, 14/3, and minus 5/3. And then it's just A times X. So it's 5236, and B was originally 2566. And the other thing is that if we choose any other x vector, that the distance is going to be larger. And that's what it means for it to be the smallest. All right. So there's one other aspect in this particular section that's kind of interesting, and that is QR. That is that if your original matrix A happens to be an orthogonal matrix, which means the columns are all orthonormal, then, or if you can find a QR factorization, then your problem might be a little bit simpler. So if you can somehow find a QR factorization, then you can rewrite your solution to the least squares problem as this. And R is an upper triangular matrix. So instead of trying to find the inverse of that, which probably isn't too bad, but instead of going through the work to actually find the inverse of R, what we could do is we can set up our equation as Rx is equal to Q transpose times B, and then your solution for X might come a little bit easier. So let's take a quick look at an example of this. And this is an example where they gave the QR factorization already. Make things easier. So suppose you have an A here that has a QR factorization, and A already has orthogonal matrices, so to find the QR factorization, it becomes a little bit easier. And our R is actually a 2x2, which we should be able to find the inverse really quickly, but we'll talk about this whole idea about back solving. So we have a Q and the R factorization for A. And let's see if we can work this out. So according to this this theorem, what we could do is we can write Rx. X is the vector that we're trying to solve for. By the way, what's the dimensions of X? So 2 by 1. Okay, so Rx is going to equal a QT times the vector B. So we got 2305, and then this is where it's important to know what's the size of your vector. In this case, it's a 2 by 1 vector. Yeah. Rx hat, I guess. All right, so the Q transpose is going to be 1/2, 1/2, 1/2, 1/2, negative 1/2, 1/2, negative 1/2, 1/2, minus 1657. So let's work out the right-hand side, and it looks like everything's going to be multiplied by 1/2 for the first one. So it's so everything's divided by 2. Minus 1 plus 6 plus 5 plus 7. What's 6 plus 5 plus 7? 20? 13? What? 17? 18. Oh, minus 1, 17. So negative 17 over 3 over 2. And then here it's alternating plus, minus, plus, or minus. So this is a plus 1, plus 6 is 7, 7 minus 5 is 2, plus 7 is 9. Is that 9? 9 halves? So the whole idea about how easy it is to back solve when you have an upper triangular matrix just says that if you write this into the actual system, we have 2x1 plus 3x2 is equal to minus 17 over 2. And then we have 5x2 is equal to 9 halves. So this is the back solving stuff that makes it easy to solve if you have an upper triangular matrix. So you just solve for one variable, and then you solve for the rest of the variables by going up. Chris? You should. Right, you should. You should know. Because the whole idea was to do this, and A is a what is this, a 4 by 2, and then X is a question mark by 1 because it has to be a vector, so it's a 1 column, and this is equal to 4 by 1. So the thing is that this is really going to match. All right, should we finish this? I guess so. X sub 2 is equal to 9/10, and then put 9/10 in for X and solve for X sub 1. 2x sub 1 plus 3 times 9/10 is equal to negative 17 halves. And I don't want to do this anymore. Let's move on. Or you guys can tell me the answer. 7, 27 plus 85. The final answer? Can we have a confirmation for that? Anybody concur? Is that okay? All right. Is that a yes, Octavio? You did it? Awesome. All right. So that's it. That's our answer. That's x bar, and that's the vector that will get us as close to b as possible. And in this particular case, we're able to use a QR factorization. I don't know if that was much easier than before, but if you have the QR factorization, you can just find these. I guess I'm finding a reason why it would be good to know the QR factorization. All right. So how many people have taken statistics? All right. And if you guys took statistics here, we're using, we've been using the same book for a long time. Chapter 10 is where they start asking you stuff about regression, correlation and regression. So that is going to be the application that we get to use here, because least squares, correlation and regression refers to least squares lines and then least squares. It's not a coincidence that that's the name that we're using here. Let's take a look at an application for the vector stuff that we've been working on. Okay, we have a set of two-dimensional points. Common problem in stats is to try to model a line that best fits the data set. So if you have a bunch of points and then you plot them, so it's called a scatter plot, and then you want to see if there's a line that best fits that particular data set. It turns out that there is a unique line that best fits, and that's going to be called the least squares line. We're going to change the notation according to how they do it in statistics. And instead of A, or matrix A, they're going to call the matrix X. Sorry, capital X. Instead of the vector X that we're looking for, they're going to call this vector beta. And instead of that B on the other side, we'll call it Y. So X is called, the matrix is called the design matrix, and beta is called the parameter vector. That's essentially the set of parameters that you're going to solve for. And then Y is called the observation vectors, which is kind of like the output. So our first case that we're going to take a look at, the simple case, is the line of best fit. And so you have a bunch of points. You want to express the line that best fits the set of data. And the line, as we know it, is y equals mx plus b. So instead of using mx plus b, though, we'll use beta sub 0 and beta sub 1. And you might have seen that notation used in statistics. And sometimes they use a plus bx and stuff. And that's kind of like what they have in the TI-83 calculators. But for us, we'll use beta sub 0 and beta sub 1. So beta sub 0 is like the y-intercept, and beta sub 1 is like the slope, mx plus b. So what we want to do is we want to find beta sub 0 and beta sub 1 so that this line will best fit the data set. So this line is called the line of best fit, sometimes called the regression line, and sometimes it's called the least squares line. All right. So let us find out the process, and the process kind of looks like this. Do you have your hand up? We could. Well, that's the neat thing about this, is that we could. Oh, my formatting's all messed up now. Just take a picture. So the idea is that you have these ordered pairs, or the pairs of points, and then what we want to do is we want to compare we have a bunch of points, and then we have a line It looks like it might be the line of best fit. Maybe that's not the right line, but let's just say it is. And what we want to do is we want to minimize the distances between the points and the line. And so for each of these points would have an x value and a y value. And then they also have I don't know if hat would be the best way to do this. That's what they do in statistics. They have a y, yo. I don't know. They have a y value, and the y value there that I've in green is the y value that you get when you put the x value into the line. And so that putting the x value into the line is called the predicted value of that point. And then the y value that you get from the actual point is called the observed value. So you have predicted values and observed values, and the predicted value would go into the equation of the line. And then the equation of the line, remember, is b sub 0 plus, or beta sub 0 plus beta sub 1 times x. And so you'll get to put in those x values, and then you want to compare that to the observed values. And you know, if this has an exact solution, then that all those points must all lie on the same line, which is in actual statistics extremely rare. So we won't find an exact solution for beta sub 0 and beta sub 1. So we want to find the closest we can get, and that's the least squares problem. So what we want to do is we want to translate the system of linear equations, because it is a system, right? We're solving for beta sub 0 and beta sub 1, and translate that into a matrix. And so the system, from a system of linear equations to the matrix, here we have our matrix X. What's it called again? A. But there's a special name we called it. Design. It's called the design matrix. And we have our, what's the beta vector called? We have a parameter vector, and then we have the observed values, or the observed vector from the y's. All right. So here's our problem, and all we have to do is try to solve it. So let's see. I think there's an actual problem here. Here we have a set of points. We can do a scatter plot of this and try to anticipate what the vector might look like. We just go ahead and try to do this problem. We have so what's our design matrix going to look like? Our design matrix is going to be ones in the first column, and then a bunch of these points in the second column, the x values. And then our B matrix, or our Y matrix in this case, is the observed values of the Y values. So we have 1, 2, 3, 4. There's 4 of them. We have the X values in here. 1, 2, 4, 5. We have our beta sub 0 and beta sub 1. And this should equal to the outputs 0, 1, 2, 3. Okay. So this is what we're solving for. Now, if you remember, we can easily jump to the solution if we remember the formula. We have A transpose times A, and then the inverse of that, and then A transpose times B. I guess in keeping with this notation, we'll call this the beta, and then we'll call this the Y vector. Hmm? Oh, I guess these are all capital X's. Bad isn't bad or bad isn't good? Oh, it's badass. No, it's just bad. Okay. So, um, this is a 4 by 2, which means when we multiply this first part, it's going to be a 2 by 2 matrix. So that's easy enough to do, right? Let's. One of them is which one's a transpose? This is a transpose. So it's 1, 1, 1, 1, 1, 2, 4, 5. Multiply that by 1, 1, 1, 1, 1, 2, 4, 5. And then we get 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 4, 5, 5, 10, 12. Is that right? Look at the next one. 12. And the last one, 1, 4, 16, 25, 46. Thank you. All right. Now this is X transpose times X. So it's a 2 by 2 matrix. We should be able to find the inverse of this, right? Remember how to find the inverse of 2 by 2 matrices? X transpose times X inverse is equal to, remember how to find the inverse of the 2 by 2 matrix? 1 over the determinant. So determinant is, oh, it's a big number. 41, 61, 84 minus 144, 48, 40. Thank you. And then switch the diagonals, negative the wings. Okay, that wasn't too bad. And now we have x of t or xt. So that's a transpose 1, 1, 1, 1, 1, 2, 4, 5 times the y vector 0, 1, 2, 3. So we get what do we get? 0, 1, 2, 6, and 2, 8, 10, 25. All right, so the beta that we're looking for would just be the product 46 minus 12 minus 12 and 4 times 6, 25. So we should probably do some, simplify this a little bit. Oh well. Say it again? The whole thing? Minus 3/5 and 7. 10. Thank you. So that's it. That's your beta 1 and beta 2, or beta 0 and beta 1. So that means if we draw the line y is equal to minus 3/5 plus 7/6 times x, and draw those points, then that's going to be the line of best fit. I guess we should try to do that real quick. So we need points. What are the points again? There we go. 1, 0. Can't see those points very well. 2, 1. 4, 2. Oops. What? So I have my points. So the line of best fit should be passing through really close to those. And so if we find our equation of the line, y equals minus 3/5 plus 7/6 times x, 7/10. That looks pretty good, huh? Looks like it would be a good line. And if we change any of these parameters, then it'll be off. It won't be the line of best fit anymore. So that's going to be the best one that we can find. Okay. All right. Now, not only that, but we can also, if you see a particular curve that, or if you see a set of points that doesn't necessarily follow a line and you have some idea that it might look more like, instead of a line, maybe a quadratic or something, then we can use, instead of the line of best fit, you can find the quadratic of best fit. And you're still using the least squares lines, or least squares method. So in the discussion in the book, they talk about this this residual vector, which is also discussed if you took statistics. The whole idea of the residual is discussed as the error. And so I don't want to go into too much of that error stuff, but I'll put it in the notes anyways. But the point that I want to get to is that we can model anything, any equation that we want. We can use any equation that we want and still be using the least squares method. And even though the equation is not linear, like if we want to do a quadratic fit, it's still going to be considered the least squares method, and it still uses linear algebra because the set of functions that you're going to be dealing with are still going to be, you can still represent your matrix. So your design matrix might look just a little bit different. So what? general modeling. All right, so they introduce an epsilon. This is the Greek letter E, epsilon, and epsilon is going to be the error that we're looking at the epsilon vector, or in this case, the residual vector that they're calling. So, but still, anything that we can write in this form can be referred to as a linear model, even though they might not look like linear functions. So we can use exponentials, we can use cubics, we can use logarithms. In this case, they're going to use quadratic. So let's take a look at a quadratic model where the equation that you want now, instead of b sub 0 plus b sub, or beta sub 0 plus beta sub 1 x, instead of ax plus b, whatever, a plus bx. Instead of that, we have a quadratic. So now we have three parameters, b sub 0, b sub 1 times x, and b sub 2 times x squared. And the parameters that we're actually looking for are b sub 1, b sub 2, and b sub 3. So what we need to do is we need to figure out what our design matrix is going to look like and what it is we're actually solving for. So because there's really not much freedom here with the b squared, it's really, controlled by what x is equal to, not b squared, x squared. So there's not much freedom in what x squared is. It's really controlled by what x you put in. We're allowed to take a look at our design matrix. It's just a linear combination of 1 times x times x squared, or not times, but So our design matrix would look like this. Now we can kind of just ignore the epsilon for the sake of just dealing with our problems because we know that we're probably not going to get the exact solution. But then this is still, although like I said, it's still linear. It's linear in the sense that the variables that you're looking at, the betas, are not being squared or not being anything. You have x's that are being squared, but those are x values that you get to put in yourself. And so our y, our observed vector, is going to be equal to our design matrix. That's going to be a list of ones, a list. These are the coefficients of b's, the betas. So ones, and then the original x's and the x's that are being squared. And then you have b and b naught. Okay? So we can use those same points and see if we can model a quadratic using this, although that probably wouldn't be a good set of points because those set of points look like they all kind of lie in a straight line already, right? Unless we change one of them. Should we change one of them? No, we could. Do I have a different data set? So this last one, what if we change the last one to have how about a 1? Maybe a 2. Getting risky. All right, so this curves a little bit now, right? So let's change that. So let's do a similar problem, except we'll change the 5-3 into a 5-2. Now, our design matrix should be full of ones again for the first term, because these are the coefficients of beta sub 0. Coefficients of beta sub 1 would just be the x values, and that would be 1, 2, 4, and 5. And then the coefficients of the beta 2 are going to be squares of each of those x values. So 1, 4, 16, and 25. Right? That's our design matrix. We have our beta 0, beta 1, beta 2, our parameter vector, and then we have our observed to be the y values 0, 1, 2, and 2. Yes. If in this case, sorry, maybe the yeah, y is equal to beta 0 plus beta 1 x plus beta 2 x squared form. Yeah. So sometimes we can use sines, cosines, and stuff like that, and then we might have to put the sign of the whatever x values or the cosine or exponentials. Chris? Hold on. And then decide for yourself on how you want to model it. Yeah, sure. All right. Yes. Oh, wait. No, that's a little trickier because you're not adding exponents. Usually it's a times e to the something, and yeah, so that maybe that's a little bit different. So scratch exponential. Yeah, the assumption. So there's another example would be like having a beta sub 0 plus beta sub 1 cosine x or something like that. As long as you can have the betas to be linear in the sense that beta is not being squared or being multiplied together by any other things aside from constants. So anyways, yeah, but cosine x, when you put the x values in, it's not constants anymore. Because you're going to put the x values from your points in there. And then so when you put 1 in, the cosine of 1 is no longer a constant. It's no longer a variable. It's no longer a function. It just becomes a constant. Well, I was thinking about e to the x. It's a times bx. Usually the exponential regression looks like this. And now if you put this to be beta sub 0 times beta sub 1 times x, now it's more complicated. You can do that. You can also do a series expansion. Then you have polynomials and stuff. Anyways, we have this matrix that I'm just going to go ahead and do on MATLAB. So our X matrix is going to be 1, 1, 1, 1, 2, 4, 1, 4, 16, 1, 5, 25. Okay. So we want the transpose times X. So X transpose times X. And we want to find the inverse of that. You can probably do all this in one shot, but of course. Inverse. X inverse. Oh, it's INV. Yeah. I'm getting mixed up with all these programs. Sometimes they use Mathematica and sometimes they use whatever. And then we want xt times y. So let's establish our y vector. Our y is 0, 1, 2, 2. And what do we want? X transpose times y. And then we finally get our we multiply the inverse times the result here. We just do it all over again. So inverse of x times x transpose times x, and then times x transpose times y. And this is our solution. Sure. So our y should equal to negative 1.3333 plus 1.5 times x, and then minus 0.1667 times x squared. Wow, they all lie in line? Can if you want. It's a joke. Are you joking? Hey, you use a calculator. Yeah. So here's the graph using the graphic calculator. So in your calculators, there's statistical commands in here that allow you to find these things. Yeah. All right. So it's 20 minutes. I don't know if this is going to work. Let's see if we can do some group work.